Okay, so now that we have a pretty good idea of what acids and bases are and some of their differences between them, let's take a look now at how they actually react with each other. So when an acid reacts with a base, we say that they neutralize each other. We say the acid neutralizes the base or the base neutralizes the acid. However you slice it, the neutralization reaction is just simply a reaction between an acid and a base. And typically, when you have an acid-base neutralization reaction, what we generally are going to see is the following. It's going to have an acid reacting with the base, and usually what we get is some sort of a salt, and then we also get water as the other point. Okay, so the salt that we see here, this is just a generic term for an ionic complex. And water is a product. You can think of this as an example of a double replacement reaction that is occurring. And we'll see why this is an example here in a second. Okay, so very simple situation. We have a hydrochloric acid which is an acid reacting with the base, sodium hydroxide, to make water and our salt. So if you take a look, and again, we apply the same thing we learned before. This is our molecular equation that we know that we've used all along. I can now write my complete or my total ionic equation. Everything that's AQ, I'm going to split apart into ions. So the HCl is made up of H plus and Cl minus. The NaOH, right, is going to be made up of sodium, Na plus, AQ, and OH minus, AQ. Now, when you have, and we saw this before, when you have a solid, you keep the solid together. You don't break it apart. Well, the same thing applies to when you have a liquid. Okay, we're going to keep that liquid intact. We're not going to split it since it's not AQ. And then our sodium chloride is our salt. That's AQ as well. Okay, so that's going to be made up of the Na plus, AQ, and then we have the Cl minus. AQ, right, so this is your total or complete ionic equation. I can now cancel out my spectator ions. What are the same on both sides? Well, I have Na plus on the left, Na plus on the right. I have Cl minus on the left. I have Cl minus on the right. Those are my spectator ions. I can cancel those out. Now what I'm left with is the following. I have H plus, AQ, reacting with OH minus, AQ to make H2O. Now that's your net ionic equation. And that tends to be the net ionic equation for lots of acid-base reactions. Right, so it is sort of like the underlying theme behind these neutralization reactions is the formation of water being the driving force for all of these. Take a look at a couple examples, and there's one wrinkle here that we throw in. Okay, so we have let's see here. So it says HCl is added to milk of magnesia, results in a solution, etc. Write the balanced molecular ionic and net ionic equation. All right, so we have our HCl acid with MgOH twice. Okay, again, trying now to predict what the products are going to be, like a double replacement. So typically your metals are swapping places, or your metals and the hydrogen are going to swap places with each other. Okay, so we swap those. Magnesium goes to where the hydrogen was to make MgCl2. And then we also get the H now combining with the OHs to make H2O. Oops. The other product. Okay, and then we have our put our state symbols in AQ, 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 and then our water here is going to be the liquid. We want to balance our equation, so we'll stick A and 2 in front of this thing. Like it's 4, so 2, 4. We need 2 here. HCl, all right, so that's your balanced equation. This is your molecular equation. We can then split everything apart. That's AQ, so we have 2H plus 2Cl minus. from this thing here. Magnesium hydroxide going to give me now Mg2 plus. That's 2 hydroxides. AQ, which why I put the parentheses in. You don't need the parentheses in. And then that's going to give now MgCl2. That gives me my Mg2 plus. And I get my 2 Cl minuses. And then my H2O water as a liquid, right? That stays the same, 2 H2O. Okay. We can cancel out spectator ions. So the 2 Cl minuses are the same. We have the Mg2 plus. That's the same. And what we're left with, we can cancel those out. What we're left with then, before we're left, this is our total ionic that we just wrote. Cancel out the spectator ions that we just did. And then our net ionic equation would be 2H plus AQ plus 2OH minus AQ to give 2H2O liquid. Okay, all these 2's are the same. We can cancel those out. Divide everything by 2. We end up with H plus, H minus, to give H2O, right? That's the same equation that we saw previously, that we saw above. Okay, so you actually want to pay close attention to what the question is actually telling you here. So it's actually saying, and that's why it's important to read the question carefully. It says that the magnesium hydroxide is actually insoluble in water. So we're actually starting off with MgOH2 solid, okay, and then that's reacting with our HCl, which is H2, all right, and then we're doing our double replacement. So again, the H and the Mg are going to swap places. So we end up with H2O liquid, and then we get the MgCl2, which is going to be AQ according to the solubility rules. And then we want to make sure that our phase is balanced, right? So we'll stick our T here in front of the H2O and our 2 in front of the HCl. And we're going to do the same thing. Anything that's a solid, we're going to keep it as it is. So we have our MgOH2S. Our HCl here, that's aqueous, so we get 2 H pluses. AQ, we get 2 Cl minuses. AQ to produce our water. We are going to keep liquids together, just like solids. We're not going to break that apart. We have 2 H2O liquid. And then the MgCl2 is AQ. We get Mg2 plus. AQ plus. We have 2 of the chlorides. The other half of that compound. 2 Cl minuses there as well. Okay, so again, we look on both sides. What are the spectator ions? Well, we have the Cl minus on both sides of this equation. We can cancel those out. And what we're left with then, so this is our molecular, the first thing we wrote, this is our total ionic. And we cancel out the spectator ions, we're left with Mg, magnesium hydroxide solid, plus 2 H pluses, which is 2 H2Os. And we get magnesium plus. Okay, this is going to be a net ionic equation. Obviously, we don't just get our salt and water in this case because our original thing was solid to begin with, but we do have something that's very similar to what we talked about previously. So a couple of things to note when we do our acid-base neutralization reactions. So we mentioned the salt that we typically form in your acid-base neutralization is an ionic compound, right? And specifically that salt from an acid-base neutralization reaction. The salt here is made up of, as an ionic compound, the anion needs to come from the acid, and the cation comes from the base. All right, so in our example that we did, first one that we did up here, in NaCl, our salt, we looked at, right, the cation on here, the Na plus, came from NaOH, which is the base, and the cation from the base, and the Cl minus came from HCl, right, which was the same. So just a quick point of clarification on that. Your acid-base neutralization to produce the salt, those are your ionic compounds, anion from the acid, the cation from the base. The other thing to note when it comes to your acid-base neutralization is sometimes, depending on what the base is, so if the base is a carbonate or bicarbonate, you get an additional product, of CO2. So for example, if I have, let's say HCl reacting with sodium bicarbonate and HCO3, okay, I'm going to get my salt and water. Okay, so now I can predict, well, I'm going to get H2O. That's my water. The salt here is going to be from the cation from the base, which is the sodium, the anion from the acid. So yes, I get NaCl. That's AQ. And then what we're saying is I get an additional product, which is like CO2 to the gas in this case. All right, and you can probably see where the CO2 is coming from. It's actually coming from this part of this. That's why you get that additional product when you have a carbonate, it has a CO3 minus ion area for the bicarbonate, which is the HCO3 minus. The presence of this thing here introduces a new product or an additional product, which is the CO2. And you will see examples of this. Maybe not in this section, but you'll see it down the road. It's important to note that that's an additional product that you get.